Hello and good afternoon to all of you. So today we'll start with the remaining topic. The next access control method that is given is token passing. Okay. So I'll discuss about some of the terms that are related to token passing. Okay. So there are some things that you have to know before attempting this particular topic. Okay. So in this token passing, there is something called a bit time or a meter time. Okay. So sometimes what happens is that they give you the times in terms of bits. Okay. So if I say the propagation time is given as 10 bit. Okay. So in if you want to convert this propagation delay into seconds, what you do, because it is length of the packet, you divide this particular time by bandwidth. Okay. So when you divide this particular time by bandwidth, you will get to know what actually is the propagation delay. Okay. So it can happen that there in this particular topic that you may have given the time in top bits. Okay. So the time can also be given in terms of meter as well. Okay, so sometimes the TP is given as 100 meters. Okay, so what can you do, because it is 100 meters is the distance, you can divide it by a velocity or the speed to get the time in seconds. Okay, so the time conversion are given as such as, so if your time is given in seconds, you meters, you want to convert it into seconds. What you do divide this particular time by band are divided by velocity. Okay, so it is given in meters, you have divided by speed or velocity. And if your time is given in bits, you want to convert it to seconds, you multiply this by a bandwidth. Okay, it is also applicable if you want to convert the second into bits, so you can multiply it. And if you want to convert seconds into meter, you can multiply it by a speed. Okay, so I can take simple example for conversion here. So suppose I ask that and your meters, so I can ask that how many meters 10 bit is equivalent to. Okay, so I can ask the question like how many meters 10 bit is equivalent to. Okay, so given the bandwidth is something like 4 mbps and the velocity is 2 into that is the speed of light, meter per second. Okay, so now because it has the bit time is converted into meters, so first you have to convert the bit into second and then you have to convert it to meters. So see, bit into second divided by bandwidth, and for second into meter you have to multiply it by speed. Okay, so now first I divide it. So what is 10 bit? I divide it with bandwidth, that is 10 raised to power 6 bits per second. Okay, so now after that you have to multiply it by velocity. Okay, so velocity is 2 into 10 raised to power 8 meter per second. Okay, so it can be, if you solve it, it should be 2 into 10 raised to power 9 over 4 into 10 raised to power 6. Okay, so you can easily find out if minus it, you will find 2 into 10 raised to power 3. So I can say 2000 over 4, so it will be around 500 meters. Okay, so again keep this particular diagram to convert the times into meters as well as into bits as well. Okay, so we can do it by if you follow this diagram. Okay, another terminology that is very important in token passing is, first is token, second is ring latency, third is cycle time. Okay, cycle time or total time, I think we use this time when we try to find the efficiency. Okay, now what happens in token passing is that token passing is like when you go towards the government center and you want to, suppose you want to update your Aadhaar card. Okay, so what you do, you take a token at a window. So when your token comes, your updation, when they call you based on your token, you go there and said that I want this particular modification. So in the similar way, in this particular thing, that if a particular station has a token, if a particular station has a token, that station will be able to transmit the data. Okay, so if if any station has a token, that station will be permitted to transmit your data. Okay, so now a token is a small message composed of a special bit pattern. It represents the permission to send the data packet. A station is allowed to transmit the data packet if and only if it possesses the token, otherwise not. Okay, so keep in mind only one token is there in the token passing. So in token passing, what happens, your station will be arranged in the form of ring topology. Okay, so I think you already know what is ring topology. Okay, so token ring is unidirectional. Uh, uh, Either it will be clockwise or it will be uh, anti-clockwise. Okay, so there will be, if you are following this, if you are transmitting this particular packet at a particular direction, there will be no collision if you are following a ring topology. Okay, I'll show you, don't worry. Okay, another thing is your ring latency. Okay, so ring latency definition is given at time taken by a bit to complete one revolution of the ring. Okay, so suppose your bit is here and it taken a whole complete revolution and arrived at the same time. Okay, so what actually be the time taken for this bit to revolve around the whole of the circuit? Okay, so now this bit will go towards this station. This station will see this bit and again put this bit onto the link, and after that station 2 will see this bit and again put this onto the link. Station 3 will see this bit and put this onto the link. Station 4 will see this bit and put this onto the link. Okay, so now the time taken first will be, what will be the propagation time to reach to take one revolution. Okay, so I'm saying time taken or ring latency is given as the time taken by one bit to complete one revolution. So time taken will be the propagation time that is required to take one revolution, plus every station will hold a bit for a particular amount of time. So bit will be seen by the station and will be put onto the link. So I'll say that if there are n station, it will be holded, this bit will be holded for bit time. Okay, so for that amount of bit time, so there is a one bit here. So to put the packet, to put one bit onto the link, whatever is that time I'm saying. Okay, so n into whatever is the bit time that is required by the station to put. Okay, so it means that this station will hold this bit for some time and again it will pass it to another station. So that amount of time is given by this. Okay, so now again if you see here, propagation time is in seconds, and this particular time is in bit time. Okay, so because there is a b here, so it means it's a bit time. So b represent a bit time here. So because it is only one bit, so I think it will be negligible, but still if it is in the form of bit time, so you can calculate it because these are two different unit. Either you can convert it into seconds or you can convert it into bits. Okay, so if you want to convert this into seconds, what can you do? This is a bit time here, it means length over bandwidth. Okay, so you can say that time is tp plus n into b over bandwidth. So that is the correct formula, or other formula can be, if you want to convert it into this particular tp into bits, so seconds into bits. So how can you convert it? Second, I want to convert second into bits. See the diagram here. Second into bits is converted by multiplying it with bandwidth. Okay, you go there, you can write tp into bandwidth plus n into p. Okay. Okay, so there are two formulas. This is also valid. This is also valid. Keep that in mind. This is in seconds. This is in bit time. Okay, so you can check it also. This is let us derive the expression for ring latency. So length of the ring is given as d. That is the distance. V n is the number of station, and the bit delay at each station is b. Okay, so there will be some delay because the bit has to go through the station. Okay, so I'm not talking about any transmission time, because transmission time is to put the packet onto the link, but there will be no transmission time because you have to the bit you have to pass through the station. So there will be some bit delay. Okay, so I'm talking about that. Okay, so transmission delay is to put the whole packet. In this regard, I'm only talking about one bit. Okay, this is the formula you already know. I've shown you. This is d by v is your transmission time, propagation time, that to take one revolution, and this is your one station hold a bit, one bit delay. Okay, so there are four station, there will be 4-bit delay. Okay, so it can be converted into seconds. So if you convert it, the formula is same that I have shown you, and if you convert it to bits, that is the same formula. Okay, so go ahead and you can look at it. It is tp into bandwidth plus n by b. in terms of bit seconds, it is the same formula here. Okay, so if you want to find it in seconds, you can again do that. Okay, so another term is cycle time. Okay, so cycle time, you may have heard this term in terms when we are calculating efficiency. In terms of efficiency, it was useful time over cycle time, or I most probably refer to it as total time. Okay, so now the cycle time, the definition is given here, time taken by token. Okay, so in this, the cycle time has a definition here, that is time taken by a token to complete one revolution of the ring. Okay, so suppose you have four station here that is connected in ring uh, ring form, that is ring topology, and this is your token. Okay, so time taken by this token to take one whole complete revolution. The previous one was when we are talking about bits. Okay, but in this particular case I'm talking about the whole token. Okay, so what happens is that when this particular station have transmitted the packet, it just passes this token to the next station. Okay, so now what is the cycle time here? So you can easily find it out. So the time taken for this token to take a complete revolution, so I'm calling this time as propagation delay. So that is obvious. So propagation delay that will be taken by this token to complete the whole revolution. So one. Another time will be because this token will pass through this token will pass through every station. Okay, so this station might hold this token for a certain amount of time until all the data packet is transmitted by this. After that, this particular station will hold the token for some amount of time. In the similar way, this particular token, this particular station will hold the token for some amount of time because it wants to transmit its data. Okay, so now that time will be n into token holding time. So n is the number of stations, so every station will hold the token for some amount of time. So that amount of time is denoted by token holding time. Okay, so now this is the cycle time, that is the total time that will be taken by the token to complete one revolution. Okay, so now if you see here, the same formula will be given here, that is d by v. D by v already you know, it is propagation delay plus n into tht. Okay, okay, delay.
Yeah, okay.
Okay, so now we come to a token passing here. Okay, so I think I have told you what is token passing. Still there are some given here, some text given here, so you can easily understand. So it is an access control method. All the stations are logically connected to each other. The access of the station is governed by the token. So whichever has the token, it will be able to transmit, and token will always be in a ring will be one. Okay, so if anybody in any station has one token, then this particular technique is efficient. Okay, so station is allowed to transmit a packet if and only if it possesses the token, otherwise it will not be able to transmit. Each station passes the token to its neighboring station either in clockwise or in anti-clockwise. Okay, so it depends upon the implementation whether you want to take the clockwise approach or whether you want to take the anti-clockwise technique. Okay, so now there are some assumptions here. The assumptions are two here. So every calculation is based on these two assumptions. So keep in mind that I'm thinking that every station have want to send some data, and each station send exactly one data packet. Okay, so the data packet, it means that one packet will always be sent by every station when it when it has a token. So there are two assumptions here. So every formula that I will calculate based in token passing is based on these two assumptions. Okay, keep that in mind. Okay, so always try to keep in mind the assumptions that are there. Okay, so if you do not remember the assumption, you will think it for a general case. So, okay, so these two assumptions are there and it will be applicable to general case, but still if you know this assumption, it means that every station is there to transmit. If they are not transmitting, the formula might differ. Okay, but I'm only talking about when every station has something to transmit, and every station will transmit only one packet when it got the token. Okay, these are two assumptions. Okay, so now how can you find out the efficiency here? So efficiency, I can easily, without looking at the formula, you can easily able to figure out the efficiency here. So efficiency will be useful time over cycle time or your total time. Okay. Useful time here, when I'm talking about efficiency, it will be useful time will be your time taken to transmit the packet. Okay. So now the, because uh, if every station receives a token, if every station receives a token, every station will transmit one packet. Okay. So when the token is at this station, it will transmit one packet. When the token is at this station, it will transmit some packet. If the token is at this station, it will transmit some packet, and same goes for this. Okay. So it means that transmission time is required.
So please make everyone an attendee.
Yeah, yeah, sure. Okay. So now it will be your useful time over the cycle time. Now, what is the useful time here? So useful time, that every station will, when it get the token, it will try to transmit. So for one station, it will be TT. For n station, it will be n into TT. So there are four station, it is 4 into TT. So that will be the useful time. And what will be the cycle time? So cycle time, we have already find it out. That will be time taken by the token to reach to the starting position. That will be the time required to travel the token from all of the stations, plus every station will hold this token for some amount of time. That will be called your token holding time. Okay. So that will be the efficiency of token passing. Now there are two strategies here. So if you see the efficiency, it is the same formula that is derived here. Now there are two token passing strategies here. Okay. So first strategy is called your delayed token reinsertion, and second strategy is called early token reinsertion. Okay. So based on the technique, your token holding time will differ. Okay. So based on that, your token holding time, if it is DTR, your token holding time will differ in case of DTR, and token holding time for ETR is different from the total token holding time for uh, DTR. So we try to find out what will be the time here. So in delayed, so you have to understand how this delayed token reinsertion works. Okay. So what happens is that, suppose this is the scenario here. Everything is written there, so you can easily read about it, but I'll explain you. Then what happens in this particular scenario? So firstly, this particular station, there are four stations. Suppose there are four stations, and this particular station is holding the token. Okay. So now this, when this is holding the station, this will transmit one packet onto the link, and this particular packet will travel onto this station, as well as this station, as well as this station, as well as this station, and come back to one. Okay. So when it come back to one, now it is the responsibility of this first station to remove this packet from the link, because I'm talking about broadcast links. Okay. So it means that when you are transferring a packet, every station that is connected to you in a ring will be able to see your packet. Okay. So you have, it is the responsibility of the sender station to take out the packet that is sent by the sender station. Okay. So that is the main concern. Okay. If the sender station does not take out this particular packet out of the circulation, it will just infinitely circles around the whole token ring. Okay. So that, keep in mind, when the packet takes a whole revolution, it will again come towards the sender station, and sender has the responsibility to take out this particular packet out of circulation. Okay. So now when this particular circle is complete, this particular station pass this token to 2, and again the same procedure will again reach that this particular second station will put the packet, that is the new packet that this particular station want to send onto the link, and it will again goes to 3, 4 and 1, and when it reaches 2 again, this particular station will take this link out of the circulation. So again, keep in mind, I am working in broadcast link. Okay, so in peer-to-peer link, there is no problem, but everything that we are doing in access control method is based on broadcast link. Okay, so now the working is there that after the station acquires a token, it transmits its data packet. It holds the token until the data packet reaches back to it. Okay, so it holds the token until this data packet reaches back to it. After the data packet reaches back to it, it discards the data packet as its journey is completed, and it releases the token and it is transferred to its neighbor. Okay, so that is the working of delayed packet reinsertion. Okay, so now why it is calling as delayed? So why it is calling as delayed? Because it is waiting for the data packet to come back to it. So it might have, when it has transmitted the data packet, it just it then can release the token, but it is still waiting for the data packet to come back to it. Only then the station will release the token. So that is why it's called delayed. Okay, so it might have released the token earlier, but it is delaying until it got the packet back. Okay, so now if you want to find out the efficiency of this, so efficiency is similar here, only the token holding time will differ here. Okay, so now if I want to find that what exactly is the token holding time for this particular scenario here. So token holding time will be, it will hold the token until the data packet will come back to it. So it means I'll require I'll require the ring latency here, whatever is the time taken to ring latency. So again, packet is just one bit that travels around and reaches at the same station. Okay, so now another one will be ring latency plus what is the amount of time that is taken by this station to put the packet onto the link. That will be my transmission delay. Okay, so now if you find out the ring latency, we have already discussed that it will be time taken by the bit to complete one circle, that will be my TP, and the bit time, that because it goes through every station, so there will be a bit delay here, that will be n into b. Okay, so again I'm saying that this particular time will always be, it's very negligible, it will be zero, it's very less, because you are holding some bit and it does not take, it takes negligible time. So I'm just ignoring this particular time and I am equating it to zero. So your token holding time will very close to TT plus TP. Okay, so you can put the value of this particular in the efficiency formula. So the efficiency formula was n into TT over TP plus n into THT. Okay, so put the value into THT, it will be n into TT over TP plus n into TT plus TP here. So you can easily understand it. Okay, so TT means that the time taken by uh, the station to put the packet onto the link, and TP is that the whole packet just take a whole revolution. So that much amount of time is your TP here. Okay, so now again you can solve it. So it can be if I solve it here, it can be TP plus n TT plus n TP. So I'm multiplying n, and you can again, this is your NTT here. Okay, so you can divide and multiply by NTT for denominator and denominator, it will be 1 over TP over NTT plus NTT over NTT is 1, and this will be NTP over NTT. Okay, so I'm dividing the numerator and denominator by NTT here. Okay, so it can be formed as 1 over 1 plus TP over NTT and plus NTP over NTT. So you can easily take the LCM, so it can become like 1 over 1 plus NTT. I have taking the LCM, it will become TP plus NTP. So I can take the TP out of it, so it will become 1 over 1 plus TP and 1 plus N. Okay, so it will be TT and N. Okay, so you can convert this TP into T2 to A here, so it can be formed to 1 over 1 plus 1 plus N over N, and then there will be a here. So A here is TP by TT. Okay, so easily you can solve it. So I've written every step. So, or you can directly see that the token holding time is this. So you just put the value of token holding time into this. So this formula is correct. This is correct. This is correct. This is correct. Okay. So I'm just simplifying it. If you are at the starting of this formula, it's also correct. Okay. So if you are directly putting the TT value here, there is no problem in that. This formula is also correct. Okay. So I'm just simplifying it. In a similar way, if you find what is exactly is early token reinsertion, so I'll take example outside of it because there are so many things going on in here. Now suppose I'm taking the same workstation. Now early token reinsertion is a very effective technique, and it is more effective than the delayed one. Okay, so I'll show you why. Now when this particular station holds the token, I'm denoting it as T. Now when it is holding the token, it will release one packet. Okay, so now when it transmit one packets, it is already being propagated. Now what it do, it transmit the token with it. Okay, so when it reaches to this second station, it will see that there is one station, one packet, and this particular station, because it receives the token, it adds its own packet, and with it again releases this token, and it is going towards this third packet. Okay, so third packet sees that there is 1 and 2, and it receives the token after that, so it will again put its own packet onto the link and releases the token with it. Okay, so the similar way, the fourth station will see that there is 1, 2 and 3, and it will put its own packet and releases the token along with it. Okay, so when this particularly when the packet reaches towards this one station, it will be 1, 2, 3, 4. Okay, so now now the token is towards this particular station. Now what is the responsibility of the station? To remove that packet that this particular station has added. It will remove it because it has the token, so it can add a new packet. Suppose I add a new packet like 5. Okay, so now this packet will move again towards this particular station, that will be 5, 2, 3, 4. Okay, so now it is the responsibility of the station to remove the second packet, and because it has a token, it will add another packet. So this process goes on. Okay, so if you are seeing here, it is more effective because in DTR, if you see at any time, there will be only one packet on the whole ring. There will be only one packet in the whole ring. But if you're seeing here, there are more packets. There are four maximum. There are four packets because there are four stations. Maximum there are four packets onto the link. So that is why your ETR is more effective and more efficient than DTR. Okay, so the efficiency is increased because it is transmitting more packets as compared to your DTR, because DTR is transferring only one packet. Okay, so that is the same thing given in the diagram here. If you understand this, this is the token, this is the packet, and then again if this station 2 transmits new packet, along with it it passes the token, and the same practice goes over and over again. Okay, so now if you see this station releases the token immediately after putting its data packet to be transmitted on the ring. So token holding time, so now if you find what exactly the token holding time in this case will be, so for this station, how much time the station hold the token, how much time the station will hold this token. Okay, so it only hold the token till the time it is just transmitting the packet onto the link. When the transmission is complete, it just releases the token. So what is the token holding time for it is only TT here. Okay, so it is holding, the station 1 is holding the token for only TT amount. Okay, so now you just have to put TT on the same formula that was I think the efficiency formula, that was N into TT, and then it was TP plus N into THT. Okay, so what is THT here? It is TT. Okay, so again, when you solve it out, it will become a 1 over 1 plus A over N. Okay, so this, if you solve it, so A you already know is TP by TT here. Okay, so you can solve it, or you, if you want to leave it here, that is also fine. There is no problem. Okay, so now see the efficiency. Now the THT here is TT, so they have equated it to 1 over 1 plus. Yeah, so you can simplify it. If you do not want to simplify it, this is also correct. There is no problem with that. Okay, so now with this you have done. There are two techniques here. First technique is early token reinsertion. The second technique is delayed token reinsertion. Okay, so keep in mind the efficiency. If you're seeing here, the efficiency for DTR, this is ETR, and the efficiency for DTR was n into, suppose I'll write the formula here. It was 1 into 1 plus n plus 1 over a over n, something like this. The formula was this, something like this. Okay, so this the n here and a here. Okay, so now see here, what is the difference between these two formula here is the numerator here is less, sorry, denominator here is less because TP, sorry, if you convert this, compare these two formulas, because there is a here. If you see here, the denominator here is less as compared to this one, because the denominator here, the term n plus 1 is added here. There is no n plus 1 term. Okay, so it means the denominator in this particular case is more. So that is why if you divide the more denominator and you divide the less denominator, your efficiency will be more here. Okay, so division is taking with the less term, division is taking with more term. Okay, so more weightage in this particular formula, less weightage in the denominator in this formula. So that is why the efficiency in this particular scenario, that is ETR, is more as compared to DTR. Keep in mind the reliability will be more in delayed token reinsertion. Why? Because reliability, because in delayed token reinsertion only one particular packet is transmitted until you got this packet back. Okay, so when you got this packet back, you are again retransmitting the next packet. So that is why the reliability in this case is very much in delayed token reinsertion compared to early token, because in early token there are many tokens that are going at once. Okay, so if you can take a look at the differences here, there are more two main differences is that early token reinsertion is less reliable, and delayed token reinsertion is more reliable. But early token reinsertion is more efficient, delayed token reinsertion is less efficient. Okay, so with this our only one technique is remaining, that is our Aloha. Okay, just let me take a look at it. Okay, so again, Aloha is, it's actually, it is not used anywhere right now. So if you are this is not, there is no practical implementation of it, because the efficiency of this Aloha is around 18 or 36%. So there are two techniques of Aloha. So the efficiency of these two techniques are 18 and 30%. 36%, that is very very less. So that is why it is not practically employed everywhere, anywhere right now. So if you are preparing for any Cisco examination, they will not ask anything from Aloha. Okay, but if it is given in your syllabus, that is why I'm discussing it. Okay, so keep in mind, it is not very important for interview point of view, or in gate also. If you are preparing for gate, they will not ask any question about Aloha, this particular access control technique. Okay, so the only advantage in Aloha is that in this particular technique, it has something called acknowledgement. Okay, so in this particular technique, acknowledgement is available. So if acknowledgement is available, then you do not have to do something like collision detection or collision uh, or carrier sensing. Okay, so this things are not required. Okay, so no carrier sensing is required, and the collision detection is also not required. So you can easily detect the collision by just, if your acknowledgement does not reach you at a particular amount of time, you can easily detect that there is a collision. Okay, so no collision detection required here, no carrier sensing required because of the acknowledgement. Okay, so when there is a collision, because if you do not reach, if the acknowledgement does not reach back to you in case of Aloha, there is you take random amount of time and again transmit the whole packet. Okay, so the random amount time is given as your back off time. Okay, so it is called back off time. Okay, now there are two different versions of Aloha. First version is pure Aloha, second version is slotted Aloha. Okay, so now pure Aloha, it's very simple. It says that you can transmit at any time. There is no problem. There is no other thing. The only problem is that when you're transferring any time, there is the chances that there will be a collision. Okay, so you have to find what will be the maximum chance, or what is the vulnerable time. Vulnerable time. Okay, so I'll write the definition. I think I have not given the definition of vulnerable time. Vulnerable time. Okay, so this is the time where your collision is possible. Okay, the time where there are collisions, where there are chances of collisions. Okay, so now if you see here, if you see the timeline here, this is the timeline. Suppose this is timeline, and at any particular amount of time, one station tries to transmit the data. Okay, so because it is everything is working in a LAN, so I'm assuming my TP is 0. Okay, so because it is less than 10 kilometer, and every signal will transfer at the speed of light, that is 2 into 10 raised to power 8. So I'm assuming my propagation time in a LAN is very very less. Okay, so now what I'll try to do, this is my transmission time that is required. Okay, so in this particular time, either other station tries to transmit the data, then there will be a collision. So this is a collision here, or some other station was already transmitting the data, and then I started transmitting the data, and then there will also be a collision. So there your vulnerable time. So if I say what will be my vulnerable time, vulnerable time is that the time where there are chances of collision. So it will be if I'm talking about this transmission time, so it can be vulnerable time can be 2 into this transmission time. Okay, so whatever time is required for transmission, in if I take double of that, there are chances in that double time that there are chances of a collision. Okay, so because at this time, if this particular TT is going to be finished, but I started here, so that is why it is again there is a collision. Okay, so now if you see the formula for the efficiency here, if you see the formula for efficiency, just wait a second. There are two cases. First cases is successful transmission, another case is unsuccessful transmission. Okay, so the transmitter is an acknowledgement from the receiving station, so this is a successful one. Okay, so another, it does not reach any acknowledgement, this is your unsuccessful one. So in an unsuccessful one, you go with the back off strategy. So I'll get back to it. Just wait a second. I was just finding the efficiency here. Okay, so the efficiency formula of given pure Aloha is given by G into 2. Okay, so if you remember, the vulnerable time is given by 2 into TP here. Okay, so sorry, 2 into TT here. Okay, so this 2 is from this particular formula. Okay, so if you can if you want to look at the derivation of this formula, you can easily go ahead and look at any site. So there are in books also, there's the derivation of this formula is given, but I think it is not that important because that is not in practical implementation. But still, if you want to look at it, you can go in books and look how this formula is derived. Okay, so now I'm just telling you a little hint here. So this that is why I've taken a vulnerable time. So this 2 is comes from this vulnerable time. Okay, so now G is the number of stations here, number of stations that are willing to transmit the data, into E. This is the efficiency that is given in case of pure Aloha. Okay, so if you want to maximize the efficiency, you already know what you take a partial derivative with respect to G and equate it to 0, so that you find the value of what is the value of G. Okay, so you will find, if you solve this particular equation, you will find the value of G is half. You put the value here, you will get that the efficiency of this particular pure Aloha protocol is 18.4%. 18 exactly 18.4%. Okay, so I can directly ask you a question, what is the efficiency of pure Aloha? So I'm talking about pure Aloha. So there are two techniques, one is pure Aloha, another is slotted Aloha. So pure Aloha efficiency is 18.4%. Okay, now if you look at this particular thing, that is back off strategy, you can I've taken this diagram from a book. You can, this is from Frozen, you can look at it. It means that how exactly this back off strategy is decided. So again, it is somewhat similar to back off algorithm. There is a little bit changes in that. Okay, so there is a timer set. Okay, so if the maximum limit for retransmission is reached, then it will not send the packet. So that is also there. Okay, so you see the flow chart here. Start, set the back off timer to 0, send the data, You send the data and you wait for the acknowledgement. If the acknowledgement is not received, it is received, then it is success. If it is not received, you again increment the back of timer, and again you check if the back of timer limit is reached. If the limit is reached, you just abort this communication and you will not transmit the packet. If it is not received, you just take the wait for back of time and again retransmit the data. Okay, so that is your flow control method. That is flow chart for pure Aloha. In a similar way, there is slotted Aloha. Slotted Aloha advantage is that what they do is they divide the time in slots, and every station will try to transmit the data in the starting of the slot. Okay, so if this particular, suppose if machine 1 wants to transmit the data at the starting of this slot, if this machine 1 what do you say, misses the starting, so it have to wait for the complete slot to get over, and it will start the again it will start here at the starting of the slot. Okay, so that is the slotted Aloha method for you, and the only vulnerable time will be this amount of time, that is your TT. Okay, so vulnerable time means at that time there is a chances of collision. Okay, so there is no collision between inter boundaries, because every transmission has to start at the starting of the slot. So other station, now the collision possible is that other station tries to transmit in the same slot, so that will be your collision. Okay, so that is why the vulnerable time now decrease to only the time slot here, that is your TT. Okay, so now see that time it divides into shared channel of discrete intervals. Any station can transmit its data in any time slot. The only condition is that it must start the transmission from the beginning of the time slot. Okay, so if the beginning of the time slot is missed, then the station has to wait until the next beginning of the next time slot. A collision may occur if two or more stations try to transmit the data at the beginning of the same slot. Okay, so only this time is your vulnerable time, that is when there are chances of collision. Okay, so now you can say that my vulnerable time is T only, and the formula for this one is changed to, there is no 2 here. So in the previous one there was 2 because it was the vulnerable time was 2 into TT, but in this case the vulnerable time is only TT, so that is why there is no 2 here. Okay, so now you check it again, equate this to maximize the efficiency. You equate this, you take derivative of this with respect to G here and equate it to 0. You will find that the G is 1, and you put the value of 1 here and you equate it, it will be 36.8%. Okay, so keep in mind that pure Aloha has 18.4% and slotted Aloha has 36.8% efficiency. Okay, so that is almost me, it is completely double the efficiency of pure Aloha. Okay, so again, these are the efficiency is still very less. It is not very much here. It is very less. Okay. So still, if I remember all the flow control methods formulas, because we have done so many formulas, and your quizzes will also take place in the coming weeks. Like in, I think you can refer to your BR for exact date. It will be 2 and 3 March, through or 3 March, I think. And you start doing start revising all the topics, because I will ask the same that discussed topics. Okay, so in this particular lectures we have discussed many formulas, but you have to try to practice different numericals yourself. Okay, so now see, we have done access control method. First was TDM. In this the formula was 1, the efficiency was 1 over 1 plus a. In TDM polling, the efficiency was TT over TT plus T pole plus TP. Okay, so after that we have done CSMA CD. So I have told you this was 1 over 1 plus 6.44a. So there were some binomial distribution, and another Poisson distribution was there also. In token passing we have done now. There are two techniques. First technique is DTR, another technique is ETR. So ETR is more efficient. It was 1 over 1 plus A over n plus 1, and for DTR it was I think 1 over 1 plus A over n. Okay, so there are so many formulas that we have done. Okay, so for Aloha, for pure Aloha, it was G into e raised to power minus 2g, which equated to 18.4% absolutely, and then there was slotted. It was g into e raised to power minus g, which equated to 36.8%. Okay. So these are all the four formulas. You have to do it yourself. That try to solve many numericals based on these techniques. So I'll introduce one numerical that is based on flow control here. Okay, so flow control. So this particular numerical is based on flow control because I know that you may have forget all the concepts of flow control. So you can solve it yourself, this numerical, but I try to solve it. So this particular numerical is a part of gate gate 2006, I think 2006 or 7 this question was asked. Okay, so now because why I've included this question, because in gate concept because in gate the concepts are very extensive. Okay, so everything that is done in flow control I have already explained you in a pretty much great detail. Okay, so if you do not remember any formula, you can still easily able to do any numerical without the need of formula, but if you remember the formula, it is well and good. Okay, so now see here, station A uses 32 bytes packet to transmit messages to station B using a sliding window protocol. So they haven't given which sliding window protocol. So they are just asking about the theoretical concept of sliding window protocol. So they have not given GBN or SR. So you assume that they are asking about the theoretical concept that I've already discussed. The RTT is round trip delay, a round trip transmission delay between AB and 80 millisecond, and the bottleneck bandwidth is given as 128 kilobytes. So you have to tell the window size. Okay, so just write all the things. So just you remember. So this is the packet size here. So I'll say length over bandwidth. I can find the TP here. Length over bandwidth is TT. Okay, so now check, this is 32 bytes. RTT means 2 into propagation delay. So I have discussed this also. So it is given as 80 milliseconds, and the bottleneck bandwidth. So bandwidth is given as 128 kilobytes per second. Okay, so kilobits per second. So it is bits, small b. Okay. So now what can I do? I have to say the window size. What is the window size here? Okay. So I have TP here. So I have TP here. So you can find out TP. Sorry. TP in this case will be 40 milliseconds. So round trip delay, you means you go towards it and come to back. This is one round trip delay. So TP will be 40 millisecond from one side, 40 millisecond from second side. Okay. So I'm saying that my TP that is given to me is 40 milliseconds. So I've taken it out from this question. Now what is my TT here? So TT is the length over bandwidth. It will be my TT. So what is my length here? Length is 32 bytes over 128 kilobytes here. So it is 10 raised to power 3. So this is in bytes. So I am multiplying it by 8 to convert it into bits. Okay. So I think it is easily, this is 128 to the 256, so that it can be easily cancelled here. So 2 into 10 raised to power minus 3, it will be 2 milliseconds. Okay, so if you know the Windows size formula, you can directly apply it. If you do not know, so what you do, you just take a little bit of time. So you know that what is my TT here? TT is 2 millisecond. What is my TP here? That is 40 milliseconds. Okay, so now 2 milliseconds will be taken by you to put the packet onto the link, and 40 milliseconds will be taken 40 milliseconds to get the acknowledgement back. Okay, so this time will be 80 milliseconds. Okay, so in 80 milliseconds, how many packets you can put on the link? Okay, so this is the main question here. Okay, so in 2 milliseconds I am able to put one packet. In 1 millisecond I will be able to put 1 over 2. In 80 milliseconds I will be able to put 40 packets onto the link. So 40 packets here and one packet here, so total I can put 41 packets onto the link. Okay, so because there is no particularly mentioned here what is the sliding window protocol, you can directly say that the window size should be 41 packets. Okay, so this you can directly say, okay, this is the answer for it. So what you packets. Again, if you know the formula, okay, so formula is this because they are asking about sliding window protocol. So it is a theoretical concept. So you will assume the maximum efficiency. Okay, so 100% efficiency, remember, for 100% efficiency, what will be the window size here? So the total time was 1 plus 2a. The if the window size or the this particular size is 1 plus 2a, then only we the 100% efficiency be achieved. Okay, so again I apply the window size. What is my window size? Should be 1 plus 2a here. Okay, so what is a here? A is TP by TT. So what is TP here? TP is 40 milliseconds over TT is 2. Okay, so again if you solve it, it is 41. Okay, so either if you know the formula you can go ahead with this, but if you know the concept, there is no need to remember the formula also. Okay, so for maximize, it means it for 100% efficiency, I will move on to this formula. Okay. Okay. So the next question is also based on this slotted Aloha. So you try to solve it yourself. Again, you can copy and paste this question. You will find the solution, but try to do it yourself before searching this particular question on the internet. The answer is already given to you. Okay. So now, if you see here, is this our all the access control methods have been done, and if you see the syllabus here also, so the first course learning objective was to explain the functionality of different layers within network architecture. So mainly we have seen the layer, that is data link layer, very extensively. Okay, so the function was framing. So I've told you each and everything about framing. Another was access control. We have done the access control, all the access control method. Another was your flow control. So I have done all the flow control mechanism. Now only error control remains. So I'll tell you in the next one. So if you see here, this is introduction. I'll share you the PPT for this one. Network structure we have done, architecture we have done, OSI done, TCP also done, layering principle, network topology we have done it. Connecting device, these are router, bridges we have already done. Physical network, we have done switching. Remaining, don't worry about it. Another one is if you take a look about LAN topology, so they will again, then topologies are written here: ring topology, token passing rings we have done, FDDI, and another thing is we haven't done is this asynchronous transfer mode, Ethernet. So these are just typical standards. Okay, so this is theory topic. I'll discuss it in one day, all the standards. There is no problems. It's very easy. The main topic in this one is your error detection and correction. So this is very important. Error control also very important. Flow control we have done, and I also discussed about this LAN protocol. So in this LAN protocol, we have discussed, actually it was access control methods, but in your syllabus only some methods are given like Aloha protocol and CSMACD. Okay, that is why I have converted this topic to access control, so that you get to know how your access control actually works. Okay, so I have discussed all the methods in access control because general questions are also there. Okay, so some topics are remaining. I also have to give you some self-study topics, so I'll try to give it in the next lecture. Okay, so now this is very important. You start learning, you start to revise every each and every topic, because it is your midterms are also coming, as well as your quizzes will also be there soon. Okay, so thank you for listening, and you can move on to the next one. If you have any doubt, you know what to do.